lasers.
Aside and stop! On the back!
Light amplification by stimulated emission of radiation. Let's go back to the Einstein years. In 1917, after special relativity was 12 years old, after demonstrating the existence of atoms, after demonstrating that light is in fact made up of particles, after revolutionizing the idea of gravity with general theory of relativity, Einstein presented us with the stimulated emission of light, a process by which an excited atom can absorb a photon and emit two photons identical to the incoming one, by jumping to the ground state. It took more than 40 years, though, to bring it to existence. But since then, the laser industry has bloomed like no other. It moved in 2020 around $12 billion and will continue growing in kinds and applications. We have lasers whose wavelengths range from 157 nanometers in the ultraviolet to more than half a millimeter in the infrared. We have gas lasers, solid-state lasers, semiconductor lasers, fiber lasers, free electron lasers, or even natural lasers. Lasers from 1 milliwatt to 1 kilowatt and can reach a few thousand kilometers of coherence length. Continuous wave lasers and pulsed lasers that reach terawatt powers. We use them to play with cats, but also to listen to music, for surgery, for telecommunications, to do basic research, to treat cancer, to write on solid surfaces, to scan products, to eventually trigger a nuclear fusion reactor. Eventually. Let's now work the details of the stimulated versus spontaneous radiation. Consider a cavity where you have an atomic ensemble, let's say a monatomic gas that each atom is going to absorb or emit photons in the same frequencies. Each atom has a quantized set of atomic transitions, and the frequency of the photons it will emit is given by nu equal to E sub n minus E sub m over h, where n is a higher energy level than m. If the gas is in thermal equilibrium at a temperature T, the number of atoms in this ensemble that are in a state m is given by the Boltzmann distribution law, and not e to the negative e m minus E naught over kT, where E naught is the ground state, the minimum energy state of the atoms. K is Boltzmann's constant. Same will happen for the number of atoms that will be in the energy state N. The ratio of atoms in energy state N versus those in energy state M e to the negative h nu over kT. Because this is a smaller than 1 number, look that the exponent is negative, it indicates that the higher energy states would be less populated than the low energy states. Atoms in an energy state M can absorb a photon and jump to the higher N energy state. On the other hand, atoms in the N energy state can spontaneously decay to the lower M energy state. Let me call A from N to M to the probability that an atom transitions from an N state to an M state by emitting a photon of frequency F. This is the spontaneous emission probability. After a differential of time dt, the number of atoms that transition from n to m can be described by d of a sub nm equal to the number of atoms in the n state, n sub n, times the time interval dt. Also, in a time interval dt, there will be a number dn sub mn of atoms that will absorb a photon and transition from m to n. This number will be dn sub mn equal to b sub mn times u sub nu times n sub m times dt, where b sub mn is the probability that a single atom absorbs a photon of frequency nu, u sub n is the density of radiation of frequency nu, and n sub m is the number of atoms in the energy state m. A and B are Einstein's coefficients. In thermal equilibrium, both populations of the energy states m and n will be stationary, that is, they won't change in time if the system is in thermal equilibrium. That means that the rate at which atoms go from m to n is the same as the rate at which atoms go from n to m. Now, this is one expression for the energy density of an ensemble of atoms in thermal equilibrium at a temperature T. Now, this should be described by Planck's formula. But it isn't. So what's wrong? What did I miss? Well, Einstein realized that something was missing here, and that something missing was the stimulated radiation. There needs to be another process in all this story that we need to include in this description. We need to include a transition from n to m different from the spontaneous one. The presence of radiation of frequency nu is going to stimulate the emission of photons. Let me call B sub nm the probability that one such stimulated emission happens. The number of transitions happened in a time interval dt will be given by this probability times the number of atoms in the state n times the energy density of radiation of frequency nu times dt. Including this in the balance equation from before, this expression should be valid for all temperatures. For very high temperatures, the right-hand side tends to 1. But as temperature gets very high, U sub nu also becomes very high. So the left-hand side becomes So for very high temperatures, the two Einstein's B coefficients are equal. Using this case back here, This is actually Planck's formula if we identify So, how does the stimulated emission compare to the spontaneous one? Well, dn sub nm stimulated over dn sub nm spontaneous This ratio depends on the temperature. That means that we will have more or less of one or the other depending on the temperature of the thermal bath, of the thermal equilibrium. For very low temperature, there will be almost no stimulated emission, which makes sense, as there will be very few atoms in an excited state. For very high temperatures, there will be mostly stimulated emission. Also, from the dependence on the frequency, we can see that obtaining this stimulated emission for lower frequencies is going to be easier, which explains why, before the laser, they built the maser, which is the same but for microwaves. Finally, U sub nu is the energy density for thermal equilibrium, but we could increase the energy density and make it larger than that for thermal equilibrium. That way we would be increasing this ratio and get the stimulated emission to overcome the spontaneous emission and obtain a laser. May science be with you.